Okay guys, this time we are going to talk about spectral clustering. This is the last algorithm that we are going to study in the family of unsupervised learning methods. As the name says, it is about clustering, but this is a very special kind of clustering. In k-means, for example, or in mixture of Gaussian models, we are looking for clusters that appears like compact clouds of points, like in this example on the left. And in spectral clustering, we are applying clustering to try to detect group of points that are not necessarily organized in groups, like in this drawing on the left. So we are, or this method, it is very powerful to detect connectivity in our data set. So it works well with clustering schemes like this one on the left, like for k-means or mixture of Gaussians, but also it works very well with kind of data sets like this. So what is the goal behind these algorithms? So given a data points or data set of n points, okay, so we are going to talk about n points, and given a similarity measure, the similarity measure could be as simple as an Euclidean distance, or as we are going to see here, it could be defined as a Gaussian kernel. So here we are going to consider this similarity between 2 points as W. And of course, this similarity should be symmetric. So the W of xi, xj should be the same as the W of xj, xi. So considering this data set of n points and our similarity measure, we want to partition the data into groups so that points in a group are similar and points in different groups are dissimilar. So we are going to work with graphs. And if you remember the notation for graphs, we define a graph as a set of vertices, a set of edges, which are the connections between each of the vertices or nodes. And in this particular case, we are considering a specific similarity function or similarity metric, W. Okay. These are we are going to call these the edge weights. So suppose that we have 3 groups of points. We need to build a matrix with the similarities weights. So if you have, for example, 10 points, let's say, you will build a matrix 10 by 10, and in each entry of this matrix you will put the similarity measure between those nodes. Okay, so for example, in this position you will write the weight of the connection between this node and this node. And of course, since this matrix is this W metric is symmetric, our similarity matrix is also symmetric. And given this similarity metric, you can also construct the similarity graph. The similarity graph, all the points that belong to the same group will have connections or edges with higher values, and the connections between nodes or vertices that belong to different groups will have smaller weight values. So in this matrix you can see like the black entries to be large numbers and gray entries to be small numbers. So these similarity graphs model local neighborhood relations between data points. One way to define a similarity similarity function is using the Gaussian kernel. So given 2 points xi and xj, the distance or the similarity between these two points is computed as the exponential of the Euclidean distance between our points xi and xj. And remember that these points can be in a higher dimension. So you need to compute the exponential of this Euclidean distance over 2 times sigma squared, where sigma is a constant that will control the size of the neighborhood. So if you increase sigma, you will increase the size of the neighborhood. Okay, and here we can see an example of a data set in which we have 2 groups of points. One is this is arranged. One group is arranged in this purple circle, and the other is in the red, purple or blue, and the other is the red points. And when you create the similarity graph, what you want to see is that the points that belong to the same group are closer in a subgraph, and points belonging to the other group are also close between them, among them. So what happens if we want to partition the graph into 2 clusters? So we are given a data set and we assume that there are 2 groups of points. So what we can do is to define a function that will allow us to decide, given 2 possible partitions, which of these 2 possible partitions is the best one. So one way to define that is using the function cut. So cut for 2 groups of points or sets of points, set A and set B, is defined as the sum of the weights that are going to connect or are connecting each of the points in set A to each of the points in set B. So here are some examples of this connection, this weight from this node to this node. You will need to sum this plus the connection with this other node plus the connection to each of the nodes in set B, and you need to repeat that for every node in A. So for every node in A and every node J in B, you need to sum the weights, the similarity weights. So the idea is that if you can find 2 sets A and B that has the minimum value of this sum, of this cut, then you have found a solution. Now this way to partition the graph is easy to solve. It requires a time which is linear with respect to the product of the number of vertices and the number of edges. However, you can get really bad solutions. For example, if we consider this cloud of points, red and blue, an ideal cut would be something like this. But with this definition of cut, you can get also very bad solutions, like for example this one, in which the algorithm has decided to create a set containing only one point. Or also this is another example of bad solution. So even though this approach is fast to compute, you can get very bad solutions. So one way to fix that is to use the normalized cut. So partition graph into two sets A and B, such that weight of edges connecting vertices in A to vertices in V is minimum, and the size of A and size of B are very similar. Okay, so what you do is you take this cut, which is this, and then you multiply it by the sum of 1 over the volume of A and 1 over the volume of B, where the volume of A is defined as the sum of all the degrees of the points in set A. So this way to solve the problem using the normalized cut is NP hard to solve. So if you want to solve it exactly, this problem is very difficult. But with spectral clustering, we are going to solve this, or a relaxed version of this NP hard problem. So we can get an approximation of the solution that is actually very good for our final goal. Now we need to understand this volume. I'm going to explain this in the next slide, but remember D for some point I or some node I is the sum of all the weights that go out from this node I and connects into every other node in the same set A. So to understand the algorithm, the spectral clustering algorithm, we need to understand three matrices. The first one is the weight adjacency matrix. This matrix W is defined as the matrix with the weights Wij between nodes I and J. So this is going to be a matrix, a square matrix, n by n, and in each entry of the matrix you will put the similarity measure between node I and J. Then we have the degree matrix. This is a big D, and this is defined as a diagonal matrix. So this is a matrix that contains only zeros, okay, except in the main diagonal. In the main diagonal, it will contain the degree of each of the nodes, okay, from the degree of node 1 or point 1 to the degree of point n. And this degree is defined as the sum of all the weights that go out the node I. So let me go back. In this specific case, when we mention the volume of A, here it says check, for example, this point here in A, the sum of all the weights that go out the node I. And the third matrix is the Laplacian matrix. the Laplacian matrix is defined as the subtraction of matrices D and W. So we are going to use this matrix L and D to compute the solutions of our spectral clustering. So we have here, keep in mind that our normalized cut is defined as the cut times this expression here. Okay, we are going to approximate this using multiplications of some vectors with the Laplacian and the degree matrix. So first consider a vector f. Okay, this is a vector of dimension n, where n is the number of points in our data set, and this is defined in such a way that in the first position of this vector we will have a number, and that number will be 1 over the volume of A if that example is in the set A, and or we will have 1 the negative of 1 over the volume of B if that point happens to be in the set B. So if you are applying this to a data set with 1000 points, this vector will be of size 1000, and each of the positions will contain either this number here or this number here. Okay, we will go back to this vector, because then you will see that this vector that we are going to obtain by computing eigenvectors in our Laplacian matrix, this is going to be an eigenvector, and that vector is going to contain the solution of the clustering. But we will go back to this a bit later on. So here we have the product of this vector f transpose times the Laplacian matrix that we defined previously times the same vector. If you develop this product, you will get to this expression here, that this product equals the cut A and B, remember is the sum of the weights, times this expression here is square. Okay, so basically we have that this product is almost the same as this. The only difference is that we have a square here. Okay, but if we compute the product of this vector f times the degree matrix times f, we get that that product equals this expression here. So if we divide this expression over this one of these will be cancelled out by this denominator, and then we will get to the expression that we initially defined as the normalized cut. And that's exactly what we do here. We define now the normalized cut as this product over this product. Okay. Okay, so now we want to minimize this normalized cut, which we are going to do it by minimizing this expression here. Remember that the vector that we defined here was of the size of the points that we have, and it was constructed using this function. If the point belongs to A, it's going to take the value 1 over volume of A, otherwise it's going to be 1 over the volume of B negative. So to solve this, we make an assumption, and this is part of the mathematical optimization problem, and this assumption is that if you compute this product here, which is the feature, the vector, sorry, times the degree matrix times the unitary vector, that equals 0. And when you solve this problem here, what you see is that what you need to find is to find a solution to this eigenvalue and eigenvector problem that we define by the product of the Laplacian times f equals some lambda value times the degree matrix times f, where you will see that f is eigenvector and lambda is the corresponding eigenvalue. And once we have solved this problem, this eigenvector and eigenvalue problem, we will see that the second eigenvector can be used for doing the final clustering of our endpoints. This is true when we are talking about two clusters of points, like in this case set A and set B. Okay. You will see that you can also apply this for more than two groups, more than two clusters, and what you need to do is to take not only the second eigenvector but also the third, the fourth, depending on how many clusters you have. So in the simplest case, when we have only two groups, we will compute or calculate the second eigenvector, and we are going to use that vector as a way to group our points. And we are going to use as a threshold the number 0. Okay. We will see that in a moment. So okay, the approximation then to this normalized cut will be through the computation of the second eigenvector. So let f be the eigenvector corresponding to the second smallest eigenvalue of the generalized eigenvalue problem. So this is an important point. When we studied principal component analysis, we were calculating the largest eigenvalues. In this case, we are interested in the smallest eigenvalues. So we are going to rank our eigenvectors from the smallest eigenvalue to the largest one. And we are going to focus on the second smallest eigenvalue. So equivalent to eigenvector corresponding to the second smallest eigenvalue of the normalized Laplacian. So this will result, or is the same as computing the normalized Laplacian, and this is equivalent to compute the eigenvector to the normalized Laplacian. So if we compare the solution that we get with this relaxed problem, which is this one on the right, we will see that it's very similar to the ideal solution here on the left. Okay, how can we understand this plot here? You will have one point that here is represented by this yellow circle. You will have one of these for every point in your data set. So if you have 1000 points, as I said before, you will have 1000 yellow circles. Each of these circles will represent the value in the eigenvector. So let me go back. Like for example, if we have 1000 points, our eigenvector will be of size n, and the value in each of these positions are the ones that they are plotting here. So you will have values that are larger, equal or larger than 0, okay, above this line, and you will have values in that f vector that are smaller than 0, so they are negatives. So these are the positions in our f vector that are negatives, and these are the positions in our eigenvector, in our second eigenvector, that are positive or 0. So this would be like the ideal solution, and this is the kind of solution that we will get with this normalized cut. And all the points that get above the value 0, like this here, will be considered to be in one group, this case group A, and all those points that are below the 0 are negative, they will be considered to be part of the other group, group B.